So give a warm welcome applause to Rafal. Rafal, the stage is yours.
Thank you. So I'm Rafał. I came from Poland, and today I will talk to you about a tool that you're gonna love, Hazelcast Jet. You will love it because it's simple and it's super fast. But first, here's our agenda for today. First, there will be the introduction. So I will talk about the basics of stream processing, and we'll tell what is stream processing, what is Hazelcast Jet, and we close this section with a kind of a hello world example, which is word count. Second, we'll go slightly deeper to understand how Hazelcast Jet works internally, and we'll close with an example of an infinite stream and with an application that reads tweets from Twitter on the fly and outputs the sentiments about cryptocurrencies. Like a sentiment is if people generally write good things about Bitcoin or bad things. And the last section will be the most pragmatic one. It will cover Hazelcast Jet features and use cases, meaning why you would use Hazelcast Jet for your company or for your pet projects or for whatever. So let's start. Actually, we cannot tell anything about Hazelcast Jet without mentioning first Hazelcast as a company. We are a distributed company, distributed in two dimensions. First, we produce distributed software, but we are also distributed because all our engineers, we work remotely. We don't have one location. I work from Poland, but we have people from all over the world. We have two products. First is Hazelcast IMDG, which stands for In-Memory Data Grid. If you've heard about Hazelcast, you probably heard about this product. This is kind of what we call a cache on steroids, because it's kind of a cache key store value, key store storage, which guarantees that the data is stored in memory. That is why it's so fast. And our second product is Hazelcast Jet, and about this we will talk today. My role is I'm a cloud software engineer, so I write code which is related to the integration with different cloud platforms, with Kubernetes, which you may have heard at the last presentation, with AWS, with Google Cloud Platform, with Azure, and so on. But coming back to Hazelcast Jet and the stream processing. So what is stream processing? Stream processing means that we process distributed data on the fly. How do we do it? We create a graph, a direct acyclic graph, which receives data on the left and outputs data on the right. And in between there is the processing. Each vertex in the graph is a piece of code, a little lambda that executes some algorithm, and the edges in this graph is how the data flows. It's Hazelcast, which means that the data input and output of each vertex is stored in the memory. That is why it's so fast. So again, Hazelcast Jet as its heart has a graph which performs the processing. In the big picture, it looks like this. So as an input for the graph, you have some source of data, which can be Kafka, HDFS, files, sockets, database. And as an output of this graph, you also have some distributed data provider. You can even write your own provider if you want it. And in between, it's Hazelcast Jet, which is based on Hazelcast IMDG. So this is what Hazelcast Jet is. for the user. You fill in the algorithm description, you specify what is your input data and what is your output data. The input data we called it a source, the output data we called it sink, and Hazelcast Jet automatically distributes the computing across multiple machines. Let's see an example. So no stream processing presentation is complete without the word count example. This is kind of a hello world in a stream processing word. The problem is that we have a long text. It can be all the books from the Gutenberg projects or just the Shakespeare books, just a long text. And we would like to count how many occurrences of each word were in this text. So basically the output is a map which maps a word to a number of occurrences. Why is it a good example in stream processing? Because it's simple to understand. Everyone can code it in 5 minutes. Because the data, the input data, it's easy to divide into, we just specify, we can just take one book for different nodes. And because the processing is actually very time consuming, it's hard to write an algorithm which will do it faster. You still have to tokenize the words and count them. So let's first think how we would write it in the algorithm in a pure Java. We'd probably come with something like that, where you have the first specify the pattern, how to regex, how to split the words. Then we start with the lines. For each line, we convert it to lowercase. Then we tokenize each line. We filter out empty words, and finally we collect it. We reduce it to a map where the key is the identity, meaning the word, and the value is the number of occurrences. We do the counting. If we were to present the flow, how the data flows for this code, it would be something like this. We start with the source, then we have the tokenize step, then we have an accumulate step, and we go to the sink. This is a classical example for map reduce. We map something, we reduce. So we can think now how could we make it better? Because this is run by one thread, by one machine. So first thing we could do is to introduce queues in between each step. Queues are always good in a distributed system. If you think about distributed, just put a queue in between data flow. This is something we can improve. Then we can actually make multiple tokenized steps and make multiple accumulate steps, still inside one JVM. It will be like using parallel streams. What we could do next is to distribute it across multiple machines, multiple physical machines. You probably noticed that while distributing, we added an additional step, which is called combine. So why is it so? Why do we need another step in our processing just because we distribute it to multiple machines? So first two steps, tokenize and accumulate, they can be executed inside one JVM. But the last one is actually, the logic is the same as accumulate. We call it combine, but the logic is exactly the same as accumulate, but it's across multiple machines. That is because we first would like to reduce inside one JVM because it's fast in memory, and the second, and only after that, we would like to send the data over the network. So we went to such data flow. So let's see how the code for this would look like in Hazelcast Jet. You may see that the code is quite similar to the Java streams. We still start from the regex, how we tokenize the words. Then we create some object called pipeline. Then we read the data from some source, from some distributed source. Then we map to lowercase, tokenize the words, filter out empty words, and reduce it to a map where the key is the word and the value is the number of occurrences. We finally put it into a remote distributed data sync. So if you look again at the pure Java and compare it, so there are only 3 differences in the Hazelcast Jet code and Java stream. Building the pipeline, so we first build the pipeline, later we'll put it into Hazelcast Jet to execute. We use distributed data source and sync for the data. So with such a simple change, we changed the data flow from sequential inside one JVM to a parallel in multiple JVMs. Let's see a demo on this. This word count is actually a demo, is an official demo on our Hazelcast Jet page. So you can look at this and run it. So if we are to look at the demo, first look at the code. So the code is exactly what we had on the slide. So we build a pipeline which do this is actually the algorithm. We can now look where we use this pipeline. So we first, that's the whole code. So we first set up, then we build this pipeline, then we put it into a job. How the setup looks like. We create 2 Hazelcast Jet instances locally. They will discover themselves automatically and form a cluster. And using these 2 instances, we send this pipeline to execution and execute join, which waits for the execution to finish. Finally, we take this data and assign it to a local variable just to print it out. So let's run it now, and you will see all the process as it goes. So we first start first Hazelcast Jet instance. It's starting here locally. It's embedded into our application. It formed a cluster with one member. Now we start the second instance, which will discover the first one by default using multicast. So it will form a cluster of two members, and now this algorithm is sent to all the members. This is our algorithm, and we finally will see the results, which is not a surprise that the most common words are the and. This example was run on all the Shakespeare books. So we've seen the first example, which can lead us to the second part of this presentation, which is to explain what is going under the hood. What does Hazelcast Jet do? We started from this graph. So when we wrote this pipeline code, the algorithm for our application, Hazelcast Jet converted this into really core graph. It's into really this direct acyclic graph, into like lower level representation, where really you had a structure like a set of vertices and edges. This is like what we call core API DAG. Actually, you could even code your algorithm in this graph way when you specify really what each vertex is and how they are converted. Because you may remember that we started from such a graph. So if a graph is more complex, you would like to tweak it a little bit, but you will rarely do it. More often you will see this higher level API, as we've seen this, similar to Java streams. But internally, Hazelcast Jet converts your stream code into this lower level representation. and then it distributes the data into each of the Hazelcast jet nodes. Distributes, the algorithm, this representation, to each Hazelcast jet node. This is important because there's a lot of things happening under the hood. First, we need to generate this graph representation from the pipeline. Then we need to serialize it. Then we need to send it to each node. Each node has to deserialize it and then execute this graph in its own JVM. And this is important because if your calculation is related to a lot of classes, maybe to a library, this all needs has to be serialized and sent over the network before starting the computation. So there can be some overhead before starting your calculation. So far, what we've seen in the first example, which was kind of a batch job. Here we had a input, which is a set of books. We send a batch job, it's executed. But the most common scenario in stream processing is actually when we have real-time data coming. For example, we can have an infinite stream of currency exchange rates coming all the time, or tweets from Twitter, which we will see in the second example, or can be some events from the event-based system, or you probably can think of many more. And if you think about it, like the infinite stream is kind of different from the finite stream, because let's take this word count example. If the input would be not the books but Twitter, for example, tweets from Twitter, then doesn't make sense even to calculate all word occurrences. What all means in that case? We could calculate all so far, but we would rarely be interested in such scenarios. So in the infinite streams, we are mostly interested in some time frame data, like what was the word count in the last hour, or what is the average exchange rate from the last 10 days, or last 10 minutes, because we want to act upon the output. And here comes the idea of windowing. So we window our data, we make a time frame in order to make some operation only on this specific period of data. This is an example how it looks like in Hazelcast Jet. So you specify you first need to add timestamps, unless they are already there from the source data, like Kafka. And then we specify the window so that all operations we execute after this are related only to 30 seconds. In this case, the window is sliding, which means that we take 30 seconds, but by 10 seconds. So the two subsequent windows overlap. So let's see an example of such a problem with infinite data stream and windowing. So our problem would be to present in real time the sentiments about cryptocurrencies. So as an input, we have tweets from Twitter coming all the time. And as an output, we would like to give the data, the sentiments, meaning if people writing good things or bad things about given cryptocurrency in the windows of 30 seconds, last minute, and 5 minutes. You can find this demo on the official Hazelcast Jet demo page. So let's see how it works. So if you open this web page, you will see that there are a lot of interesting demos on Hazelcast Jet. There is something about image recognition, flight telemetry, about the trading. We'll look at one of the demo, which is Twitter cryptocurrency sentiment analysis. When you open this, you have the algorithm here. So we first read the Twitter source, then we add timestamps to the data, then we will filter only the relevant cryptocurrencies. And finally, we will calculate the sentiments and show it in 3 windows in 30 seconds, 5 minutes, and 1 minute. And we should see the table with the output. If you go to the GitHub page, you can even see more. The GitHub page of this demo, you should see even more interesting data and the way how to run it. Actually, is super easy. You just run Maven, exec Java. So let's first see the code. The code is exactly what with the algorithm we've seen right now. So we read the stream of tweets from Twitter. We add timestamps. Then we take only the tweets that are interesting to us about cryptocurrencies. Then we calculate the sentiments about them. And finally, to this stream, we apply 3 different windows. First is by 30 seconds, by 60 seconds, and by 5 minutes. Each one is sliding by 10 seconds, which means that the output data will see every 10 seconds. This time we will run it only on one Hazelcast Jet instance, but if you just run more of them, you will experience the parallel execution. Here you might be interested in the dependencies. So for analyzing the sentiments, we use the natural language processing library from Stanford, and for reading the tweets, we use the SDK library from Twitter. If we run it, first we will we will see the one Hazelcast Jet instance starting. So this time we had only cluster of 1 instance. This is our algorithm that is sent. This lower level, this DAG representation of the algorithm that is sent to each of the node of Hazelcast Jet. And in a second, we should see the results of our cryptocurrency analysis. And each second, there will be a new table. As you can see, like, the interesting is that people, in general, they're writing bad things about cryptocurrencies, which may mean that they will lose the value. So this is our second example for this presentation. Let's move to the last section, which I promised to be the most pragmatic to you, which will tell about Jet features and the use cases. You may remember that I said at the beginning of the presentation that you're gonna love Hazelcast Jet because it's simple and fast. Actually, the easy to use and the performance are the core values when we create features in Hazelcast Jet. It's something that we think deeply about. You've already seen how easy it is to use Hazelcast Jet, that it's almost as easy as writing Java streams. But what about the performance? We publish performance result, the benchmarking, on our blog post, and the tools how to recreate them. So you may have a look. For this word count example, this is a graph for the word count example, comparing Hazelcast Jet to Apache Spark and Flink. The green, the fastest one, this represents how many megabytes of this word count per second each framework processed. The green one is the Hazelcast Jet when the source data and the sync data is IMAP. IMAP is a structure from Hazelcast IMDG. So the green one is if everything you use is inside Hazelcast. Then it's super fast, but even not looking at this one, just as the data comes from any distributed source, you can see that Hazelcast Jet is almost always at least twice faster than the competitors, which is good for us. Measuring not the throughput but latency, this graph is for the trading example about trading data. So here is, because when you have an infinite stream, you're usually more interested in the latency because you have some limited data scope, but the time that you wait for the results is important. Because in case of trading, you probably, there's milliseconds, how many milliseconds you wait for the results are important because you would like to do something based on the results of a calculation. So here also is like Hazelcast Jet is better actually than the competitors. Speaking about other Hazelcast Jet features, in the first two examples, we've seen that Hazelcast Jet works nicely when it's embedded into your application. So we didn't start any server, we just had start the instance directly from our Java code. But you can also start Hazelcast Jet as in a client-server architecture. So you start your your cluster with Hazelcast Jet. For example, in the cloud, you can start it on AWS, and then you just use client application to connect to the cluster. This we're gonna see in the last example for this presentation. We also support a discovery in multiple platforms. So members discover themselves automatically not only on local host or by multicast in the local network, but we have plugins for multiple cloud environments so that you just run your Hazelcast Jet instance on, for example, AWS instance, and it automatically creates cluster with your other Hazelcast Jet instances and other deployed on the other EC2 instances. So you may think that it's nice tool and it can be useful in some use cases, but where could you use it? So the first use case, I see like two use cases for Hazelcast Jet. First use case is quite obvious. So if you work on the big data project, then you may use it in your project. But the second use case is, as I see Hazelcast Jet, is maybe a little less obvious. I would say you can use it just everywhere. I mean, when you need a speed up, because it's so simple to use, so why not to use it everywhere? And here, let me tell you the story like which happened to me 2 weeks ago. 2 weeks ago, my wife came to me and she wanted me to write a web crawler for her. She didn't express it that way, but it was basically what she wanted from me. Because my wife, she loves traveling. Actually, we both love traveling. That's why I have a remote job. We just travel and work around the world. And she it's not only about traveling, but she also writes about it. Write a blog post about travels in some traveling portal. And she came to me 2 weeks ago saying that, you know what, this portal is going to shut down in 2 weeks. And I don't have any backup copy. So can you write for me some script to extract this data, my own blog post, so I have a backup? So I wrote it in Java as kind of a script for her to web crawl or her blog posts. And I ran it, and it took 12 hours. The reason for that, it was not actually the performance, because it's not super performant consuming, but the reason for that, there was some throttling per IP addresses on the server side. So you couldn't make more than 10 requests per second from one machine. So I thought, I'm working on this Hazelcast Jet. Why not to set up a cluster on AWS and just set like 9 machines with different IPs, and they will form a cluster and send my calculation there. And that's what I did, and that's the part of our last example for this presentation. So the problem is to parse the post from the web page. The input is the URLs for the trips, and the output is the content of the blog. I uploaded this to my GitHub so you can have a look at the code if you're interested. Let me quickly show you how it works. Let me first show you the source code, which is actually the least interesting in this example. But we just again create a pipeline, read from some URLs, then take from the trips, take the blog posts and read them and give them to some output map. What is the most interesting is how it's deployed on AWS. So this time we'll use this client-server architecture. So I will have a server on AWS. So I start 9 EC2 instances. When they start running, I'll connect to each of them and start Hazelcast Jet. This time I started manually using SSH and start an instance on the instance. But obviously, if you can run it Hazelcast Jet as a Unix service, and then it will start automatically. You don't see anything, but it's like SSH to the. It will be bigger in a second. Yeah. So SSH to this EC2 machine. This is the configuration for Hazelcast. It's like all you have to specify it to make it work on AWS is just AWS enabled true and the region, and then the Hazelcast Jet members will discover themselves automatically. So when I start the first one, it formed the cluster of one member, and then if I start the next one, they will join the cluster. So while starting the last one with exactly the same command, with exactly the same configuration, it will discover the 8 instances already running, and they will form a cluster. So there's no specific configuration. You just say an AWS enabled true, and then you have a cluster of 9 Hazelcast Jet instances. Then I can use the client side, so my algorithm, and start my application using exactly the same Hazelcast Jet AWS plugin. It discovers where is my cluster. So there is no static IP configuration here. Discover where is my cluster on AWS. It joins this cluster as a client and send the computation to the cluster. And you can see that on each of the machine, part of the data is being fetched, and that's how and then the data is collected back to the client. So the nice thing is that you don't write any code on the server, you just have everything in the client, the algorithm is serialized, and that's how it's distributed. So this was our last example for this presentation, and actually the last thing I wanted to show you. I hope you like Hazelcast Jet. I hope you will try at least these demo samples, which are super interesting. And thanks for attending this. Thank you. Yes.
Do we have any questions? I see 2 hands raised.
Hi, Rafal. Thank you for your talk. I have 2 questions, actually. One is, you mentioned, like, is it fair to say that everything happens in memory? And, like, if yes, how does Hazelcast Jet handle, like, node failure? And the other thing that you mentioned that we send to every node a copy of the DAG of the pipeline. Why do we have to send the whole thing? Like, why does the node needs to know about this? Like, isn't there a master that only needs to handle this and distribute the workload in the nodes? Thank you.
Okay, thank you for the questions. So let me start from the first one, which was about how if everything happens in memory, then what was about what if everything has happened? How do we handle like the node failure? Yeah, that's a very valid question because the node can fail. So we do some smart things, which were it was not a fit for this presentation. But what we do basically is we snapshot the data from time to time over all the nodes. So, and then we replay all the events which came after. So imagine like that the one node fails. Yeah, and also we have the backup of the copy. There's always one more. There's always the node that keeps the data, like the input and output for the vertex, but also a backup for this on another node. So if one node fails, we still have the data. We make snapshots from time to time. Then you have to replay part of the data. So if there is a crash, we take it from the backup node, the data, and we replay from the last snapshot. Did it answer your question? Yeah, so also it's configurable because by default we keep just one backup, but we can have more because if everything is memory and you have just one backup, if by any chance two nodes fails at the same time, then you have a problem that you will never retrieve it. However, we do like in terms of AWS and GCP, we do smart things like that. Your backup is never kept in the same zone, availability zone. So if the whole zone fails, you still have the backup. And your second question was, could you just repeat?
Why do we have to send the copy of the dark in the node? Why does the node need to know about the whole dark, not just the work that it has to do by itself?
Yeah, because the node, because each node is not only about one vertex executing one part of the algorithm, but each node executes like, coming back to our word count example, where we had tokenize and reduce and counting. So each node does both actually. It tokenizes and do reducing. So it needs to know like that first we reduce inside the same JVM and then we combine across multiple nodes. So it needs to know the whole, the algorithm for each vertex and how the data flows. Because one vertex is not one physical machine, it's not one Hazelcast Jet node. Is it, does it explain? Okay, thanks.
Thank you very much. Here is an olive tree from Plant Box.
Thank you.
Give a warm applause and let's go to our next speaker.